about bases. And in particular, last time we talked about change of basis. So now not only do we know what our basis is, which is a linearly independent spanning set of vectors, it also tells us the dimension of the vector space that we're dealing with. And we can have several bases that represent vectors from a single vector space. And so we discussed ways to transition from one basis to another basis using a transition matrix transition matrix that can go from one basis to the other and vice versa. And we learned that the transition matrices themselves from one base to the other and vice versa are inverses of one another. And we're able to compute the transition matrix by creating a matrix where one of them is the one one square submatrix of that big matrix. On the left is the new basis vectors, on the right is the old basis vectors. And you perform row reduce. We perform Gauss-Jordan elimination to convert that matrix into row reduced echelon form, and then the left side becomes identity and the right side becomes the transition matrix. So it became very much more computational than the beginning of vector spaces. In the beginning of the lectures on vector spaces, much more theoretical. And then we headed towards bases, and then it became very computational. And now we're going to kind of go back to the more theoretical side of things with respect to bases, and in particular, some new kinds of vector spaces. So we're going to be discussing row space. So let me call these matrix spaces. The ones that we're going to be discussing are very fundamental. So the first one is a row space of A. Is there? So the row space of A is a subspace of Rm. Spanned by the row vectors of A. By the row vectors of A. Now recall that a matrix A, I should say, an M by N matrix A is a linear, or represents a linear transformation T. Remember this? That goes from Rm to Rn. And so then that's why we have this matrix A. When it's called the linear transformation, when we go from Rm to Rn using a linear transformation, then we can create a matrix A. This is A1, A12 all the way to A1n, A21, A22 all the way to A2n. This goes all the way to AM1, AM2 all the way to AMN. And the idea is that the row 1, row 2 all the way to row m, the row space, so i.e., in other words, the row space of A is the span of the row vectors R1, R2, Rm. It's the span of those row vectors. So if you take all these rows and treat them as vectors and you create a span, that span will be considered the row space of A. That's one of them. Second one is the column space. Column space of A. And as you can tell, remember A is m by n. So so pardon me, this should be not Rm but Rn. So these things these little letters matter. M and N matter. So the row space of A is a subspace of Rn. Why is it a subspace of Rn? Because everything in the row, there's m rows, right? There's m as in Minnie Mouse. There's m rows, and each of those row vectors have a total of n as Nancy, n entries. So all of these elements are in Rn. The rows are elements of Rn, and that's why it's a subspace of Rn. But the column space, the columns are here, all have m elements in them. So this will be a subspace of Rm. This is spanned by the column vectors of A, meaning that the column space of A is equal to the span C of, call it C1, C1, C2, all the way to Cn. So I'm saying C1 here, C2 here, and Cm. Sorry, Cn. There's n of them. So we have n columns and m rows. Okay, and the last one is called the null space. We talked about this already, right? The null space of A. It's also known as the kernel of the transformation in more general terms, but it's a subspace. It's a subspace. Now my question to you guys will be, which subspace is null space in? Is it in Rm or in Rn? M or N? What do you guys think? N. Now, why do you think it's N? And for shorthand notation, guys, instead of writing row space of A all the time, you can just write row and then row A. This represents a column space. Okay. So I'm gonna write this denoted by and then same thing with the column here. Instead of writing this whole thing, I just write COL of A. So, Baldwin, why do you think the null space of A is a subspace of Rn? I'll leave it blank for now. Um, it's also known as the solution space of the homogeneous system AX equals 0. So the homogeneous system, remember this? It's the system where you equal the product of the matrix with a vector. We equal that to be 0. So the solution space or the null space are all the vectors x that when you plug it into this equation gives you 0 for A when you multiply it by A. That's the null space. It's all the x values. So in other words, the null space of A is equal to all the vectors such that AX equals 0. So if you are a column vector that multiplies to A gives me 0, then you're considered in the null space of that matrix. Now, is this a better reason? Does this better understand? Now, with this definition, is it better understood as to why the null space of A is a subspace of Rn and not Rm? Why does it have to be Rn, not Rm? What's A?
Because multiplication looks at the multiplication looks at the second matrix has to have as many rows as the first matrix has columns.
Correct, because the very nature of matrix multiplication requires that the number of columns in A has to match up with the number of rows in X. So X has to have n rows, n, in order to in order for the matrix multiplication, which embedded in it is the dot product. So in order for the dot product to occur every single time, meaning that the row of A dot product with X, in order for that to be defined, X would have to have an n number of them. So if you have n entries in X, if X has n entries and it's a column vector, then that means that X belongs to Rn. So then to make that explicit, I'm just gonna make sure I say that X is a member or belongs to the set of Rn. So that's very, very important. The null space of A are all the vectors X and Rn such that A times that vector gives me the 0. So these are very important matrix spaces, which we have seen already, but now we're formally writing them down and defining them. So for every matrix A, we have a row space. For every matrix A, we have a column space and a null space. Okay. So once we have that established, a few things to just note, right? And I've talked about this in the beginning of when we discussed matrix multiplication, but I just want to emphasize it once again, that whenever you have AX, right, equals B, the matrix multiplication of AX can be also interpreted as a linear combination of the columns of A. So what am I saying by this? AX, right? When we write this down, this can be written as let's call this let's call this A1, A2, A3, AN. So all these are the column vectors of A, right? And I multiply it by x1, x2, all the way to xn. When I perform matrix multiplication, I can also treat it as x1 being multiplied by a, the vector, the column vector a1, the first column of A, and then x2 times a2 plus dot 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 all the way to axn an. So when you solve a matrix equation that we've been solving for the past several months, matrix equation, when we're asking what column vector x when you multiply by the matrix A gives you the vector B, another way to reformulate that question is saying, is the vector B in the rows in the column space of A? So this is what I'm saying. The question or problem of finding x so that ax equals b can be reformulated to the problem asking if b is in the column space of A. Or in other words, is B in the span of the columns of A, the column vectors of A. Any questions about this? This is very important to make that connection. The column space of A is the span of the column vectors of A. And the question AX equals B is asking whether or not B is in the column space of the matrix A. And if it is, then it could be written as a linear combination of those column vectors of A. So it's not simply just, let's find X by multiplying by A inverse on both sides and move on with our lives. It's also, what are the coefficients for these vectors of your matrix A that when you find those scalars and you apply it to this linear combination format, it equals exactly what B is. So that's more of a theoretical connection rather than just simply a computational reality that X, the entries in X makes this matrix equation work. It's beyond just making it work. It's saying that B is in the column space of A if the solution exists. If it doesn't, then it's not in the column space. So that's another way to think about it. Okay, so that's pretty important. Okay. So once we've made that connection as well, column vectors or the span of the column vectors is the column space, and the column space is inherently embedded in this question ax equals b. Is the vector b in the column space of A? That's what we've been asking this whole time. Okay. Now let me do one more. Let me do an example that connects the homogeneous with the non-homogeneous system. Okay, so a connection between homogeneous and non-homogeneous systems. And homogeneous is AX equals 0, and non-homogeneous is AX equals B, right? When B is not 0, when B is not necessarily 0. That's what a non-homogeneous is. Okay, so suppose that x1, x2, x3, and x4 is -1, 2, 4, -3. Or in other words, the column vector x is -1, 2, 4, -3. Suppose this is true, and this is a solution, is a solution to the non-homogeneous system AX equals B. Okay, so we have a solution, and the solution is AX equals B. And we also suppose that, the solution set or the null space of A is given by, so remember what the null space of A is. It's the solutions to the homogeneous system AX equals 0. And suppose that the null space is given by x1, x2, x3, x4, -3r plus 4s, r minus s, r and s. Okay, so we have this. Or in other words, x is equal to -3r plus 4s, r minus s, r and s. Okay, so what are we given? We're given a solution to the non-homogeneous system, right? This is the non-homogeneous system. And then we're also given solution to the homogeneous system. And so the first question is find the solution in, find the vector form of the null space of A. Or in other words, find X such that AX equals 0. So we kind of already did that here. But as you notice, there's a lot of R's here and S's, right? What are the R's and S's here called?
Free variables.
Right. These are the free variables. So R and S are the free variables. We sometimes call them the parameters as well. So which ones of these are the free variables? Out of x1, x2, x3, x4, which are the free ones and which are the non-free ones?
X1 and X2 are the free, and X3 and X4 are the non.
Well, actually, it's the opposite.
Oh,
X3 and X4 are the free ones. They're the ones that do not depend upon any other of the variables. They can be anything. What are they? Well, just call them R. X3, call that some number. That's what it's saying. This could be 100. And what S is? This could be 2. Now, the moment these numbers here, these variables here are defined, the moment you define them, X1 and X2 are predetermined because of these. So these are the pivot variables. These are the ones where you're gonna, if you perform row reduced echelon form, you will see the leading ones in the first and second columns, and everywhere else it would be zeros, right? The third column, the third row and the fourth row, you would have zeros. So these are the pivot variables. So when you want to find the null space of A, you have the vector negative 3R plus 4S, R minus S, RS. But if you just leave it this way, and we say such that R and S are scalars, right? They're all the possible scalars that exist. Or instead of doing that, what do? We reassociate them. We kind of separate these columns here. And how can we separate this negative 3R plus 4S, R minus S, R and S? So split this up with as vectors that have only R's in them and a vector that only has S's in them. So this becomes negative 3R, R, R, 0, plus 4S, negative S, 0, S. But in the first column vector, we have a whole bunch of R's that can be factored out, and I'm left with negative 3, 1, 1, 0. Factor out all the S's, and I get negative 4, negative 1, 0, 1. Sorry, not negative 4, positive. So now I can write this as the following. R negative 3, 1, 1, 0 plus S 4, -1, 0, 1, such that R and S are real valued scalars. Does everybody follow this? Does everybody see what's going on with this? So again, this is just based upon the information that's given. So we're given that the solution space is defined in this manner. We recognize that there are two free variables, and we're able to now write the null space, which is the solution space of the vector of the matrix A. We're able to define the null space as a linear combination of these two vectors. So what's an equivalent way to write this? I also write this as the span. This is the span of the vectors -3, 1, 1, 0 and 4, -1, 0, 1. So the null space of A is the span of these two vectors. And what's also notable about these two vectors? Beyond the fact that they span a subspace of Rn, or in this case, it would be R4. So you see all this information we can glean off. So the null space of A is a subspace, note, is a subspace of R4. So the null space is a subspace of R4. It has two vectors that span it. And are these two vectors linearly independent or dependent? What do you guys think? Yeah, they're linearly independent. You can verify that very easily. How can you verify that? With two vectors, they're linearly independent because of what reason? When you have two vectors, it's very simple to determine whether they are linearly independent or not.
If one is a scalar multiple of the other one.
Right. So they're linearly independent because neither are scalar multiples of the other. Neither are scalar multiples.
Could we also say they're not within the span of each other?
Very good. That's right. Equivalently, that's exactly what it means to not be a scalar multiple of the other, is that neither is in the span of the other. That's a very good connection. Equivalently, neither vector is in the span of the other. That's what it means to not be a scalar multiple, and that's what it means for two vectors to be considered linearly independent. So if you have a subspace that is spanned by two linearly independent vectors, what's the conclusion? What can you conclude about these two vectors? If you have a spanning set and that set has vectors that are linearly independent, they're called a what? That's right. Therefore, the vector -3, 1, 1, 0, or I should say, therefore, the set -3, 1, 1, 0 and 4, -1, 0, 1 is a basis for the null space of A. Right? So we're putting all the stuff we've learned all together. Now, since we know that the basis is two vectors that span and are linearly independent, that span the null space A, so then what would be the dimension of the null space of A? What would be the dimension? Eight. Whoa. That's a lot. You can't have 8. You can't have a dimension of a subspace be 8 if the overlying space has dimension of 4. You can never have more. A subspace can only have less. Yeah. So remember, a basis is the number of things, or the number of vectors in a basis tells us the dimension of the space. So the dimension of the null space is 2. And so we have more terminology here. So the definition that I want to introduce here is the definition of the nullity. So the nullity of A is the nullity of A is the dimension of the subspace of the null space. So I would say the nullity of A. So every single time you see the word nullity, we're speaking of the dimension, okay? So that's the next thing that follows. Okay, so that's kind of hopefully pretty clear and straightforward from the given information. So we're given the solution in general, right, is defined by this vector, and then we're able to split it up and we're able to see what that null space really looks like. It's the span of these two vectors. And the span of two linearly independent vectors creates a basis. And so the basis tells us that we have two vectors, and hence the dimension of that vector space, or that subspace, the null space of A, is exactly 2. Okay. And part B asks, find the general solution to the non-homogeneous system. AX equals B. So we were given that the solution was what? The solution was -1, 2, 4, -3. So it was negative. So if A, if you multiply it by -1, 2, 4, what was it? -1, 2, 4, -3. If you multiply it to this, you get the vector B. And we didn't specify what B was, and we didn't specify what A was. We just knew that when we multiply this together, we get B. So the question is, what's the general solution? Now, this is interesting because this is what's called a particular. This is called a particular solution. This is the particular solution. And how is this related to the null space? So if I consider this as the particular solution, I'm gonna call it denoted by x naught. So that means that A times x naught equals B, right? And if we let V, right, let V be some number, some vector in the null space of A. What does it mean to be in a null space of A? It means that AV equals 0, doesn't it? That's what it means. So if you have a vector in a null space, then when you multiply by A, it gives you 0. That's what it means to be in a null space. So then what happens when I do this? What is this supposed to give me? Does everybody follow what I'm doing? So AX naught equals B, AV equals 0. What is A multiplied by X naught plus V supposed to equal? The X naught space. I'm not sure what you mean by the X naught space. I think I know what you're trying to say. I think you're saying the solution space of this, right? So yeah, it wouldn't be called the X naught space. It would be referred to as the solution space of this equation. But my question is, what does this give me? When I multiply A by X naught plus V, what is the result? Which I think you should be able to know if you know the null, if you saying that this is the X naught space. When I multiply this by this, what do I get? What do I fill in here? Anybody here? So what happens when I distribute the A, for example? I can do that, right? I can do AX naught plus AV. Well, AX naught, I said equals B. And what does AV equal? 0. But what's B plus 0? B. So wait a minute. AX naught equals B. Remember what X naught was? The particular solution. What was V? V was a vector in the null space. So if you add something if you add the particular solution to something in the null space, you get a new solution to this system. So then what I'm going to do is I'm going to rewrite V in terms of a linear combination of what? Of these vectors. So V is a linear combination of the basis vectors of the null space of A. So X naught V naught, this thing here, this is called the general solution of non-homogeneous system. AX equals B. So then what is that general solution? What does that look like? Well, it's going to look like X naught. What is X naught? -1, 2, 4, -3, plus R of what? R of -3, 1, 1, 0, plus S of 4, -1, 0, 1. And this is the general solution. I hope everybody sees what's going on. So the general solution to the non-homogeneous system AX equals B is the particular solution plus a linear combination of the basis vectors in the null space. So if you include the null space plus the particular solution, you have the general solution. These vectors here, when you multiply by 8, doesn't influence the computation. It will always give you something with 0. These will always be 0 when you multiply by a. This is the only thing that becomes, when you multiply by a, becomes the vector b. But the idea is that now, if I find one solution, is there more? In this case, there are more. And you can write this infinitely many ways because you can write, you have two scalar vectors r and s here. So any questions about this? One second, guys. I have to do. I think my door is slamming outside. Just give me 1 second. Yeah, sorry about that. I resumed the recording now. What's the first order of business here? What's the first thing we should do here to solve the system? We create the matrix equation, right? So then the coefficient matrix would be what? 1, 1, 2, 1, 0, 1, 2, 1, 3. This is x1, x2, x3. This is 5, -2, 3. Right? And then what do we do? Get your x1, x2, x3 values, right? So then how would you do that? How do we normally do that? Inverse, right? Inverse, okay. So do you notice anything about this particular matrix A? Is it invertible? Can you tell something about those rows? Do you see something about these rows here? Sum, right? 2 plus 1 is 3. 1 plus 0 is 1. 1 plus 1 is 2. What does this indicate? This indicates that the rows, right? We see that, notice, row 1 plus row 2 equals row 3. What does this mean? This means that row 3 is what? Is in the span of what? R1 and R2, correct? So if it's in the span, what does that mean? We have a free variable, good. Right, right. This means that R1, R2, R3 are what? Linearly dependent, correct? They're linearly dependent. The first two rows are linearly independent. The moment you put that third row in, it's linearly dependent now, a linearly dependent set. Linearly dependent set of rows indicates that the determinant will be what? 0. Do you guys see all of this? Do you see how everything kind of like meshes together? The determinant is 0. Why? Because remember when you do the row reduced echelon form, if I were to do that, I would have a row of zeros. And row operations, such as adding a scalar multiple to another equation, does not affect the determinant. So if I were to do that and have a row of zeros, the determinant of that matrix with the row of zeros would be 0, which would imply that this original matrix is also determinant having 0. If the determinant of this matrix is 0, then it means that this is a non-invertible matrix. The inverse doesn't exist. It doesn't mean that the solution doesn't exist. It just means that there is no one unique solution. It may or may not be. It could be no solution at all. But there is no one particular solution because there's no inverse. There's no one unique solution. So what do we do instead then? What if we can't do the inverse of a matrix A, then what do you do instead to try to still solve this equation? And this goes back to the beginning of the semester. You see now everything's going to come back full circle. So we have to do row reduced echelon form and we have to augment the matrix. So I want to find the matrix now is going to be 1, 1, 2, 1, 0, 1, 2, 1, 3, and the column will be 5, negative 2, 3. Right? And then we're going to do row reduced echelon form of A, B. So what do I get? Well, let me put this in my calculator. Let me do second matrix. Three by 4. So we got 1, 1, 2, 5, 1, 0, 1, negative 2, 2, 1, 3, 3. And then second matrix. I'll do second quit, second matrix. We'll row reduce echelon form. A, and look what I get. I get 1, 0, 1, negative 2, 0, 1, 1, 7, 0, 0, 0, 0. So I hope now that question that was asked in the very beginning, what's the point of row reduced echelon form? Does it really matter in the grand scheme of things? Well, hopefully now I start to see how essential it is to solving systems of linear equations. So immediately we already knew that x1 and x2, right? We already knew that these column vectors, or that we were going to have two pivot variables, and we're going to have one free variable, right? Our free variable was x3. So then when we solve this, what do we get? We get x1 is equal to, I should write it like this, x1 plus x3 equals -2. And we get that x2 plus x3 equals 7. So x1 is equal to -x3 minus 2. And x2 is equal to -x3 plus 7. What's x3? Well, x3 is something, call it t. And then this will be t, and this will be t. Do you guys see that? So then from here, what would be my quote unquote solution to this? What would be my solution? It will be -t minus 2, -t plus 7, t. And then what do you think I'm going to do after this? Am I going to leave my solution this way? I want to learn more about my solution. So how much more am I going to learn about my solution? Can I split this vector a bit, where I have a whole bunch of stuff with t's and everything else with no t's? So what is that going to look like? -2, 7, 0 plus -t, -tt. And what is this? -2, 7, 0. What is this? And the t's that I can take out, what does this become? What did I just figure out? This is the general solution of ax equal to b. Now, can you tell me more about these vectors? What is this vector? -270 is what? It's not the general solution, but the right. This is a particular solution, also known as, like, we usually call it x naught, right? Of the homogeneous, non-homogeneous system. Correct? So that's the particular solution. So if I plug this in, into here, so if I plug in -270, this would make it equal. This would be a particular solution. And then what is this? What does this one here represent? The null space. Right. This is the null space. That's how general solutions of non-homogeneous systems are formulated. They're formulated as a particular solution plus a vector in the null space of A, because we know that the null space consists of all the vectors that when you multiply by A give you 0. So if I multiply this by A, so if I plug in -1, -1, 0, or any scalar multiple of that vector, 1, 1, I should say, not negative 1, 0. Negative 1, 1. If I multiply this, I would get 0. And this number, this vector is the basis of the null space. So what does that mean? What is the nullity? What's the nullity of A? Meaning, what's the dimension of the null space? Well, there's only one vector in the null space of A that spans everything in the null space of A. So the nullity is 1. So what's interesting is that the null space of A, the nullity of A, the dimension of the null space of A is related to the number of free variables. So in this case, there's only one free variable. So the nullity will be 1. So I have to make that connection as well. The number of free variables that exist in the row reduced echelon form of this augmented matrix tells me the nullity, tells me the dimension. So any questions about this? So we know a lot more now, hopefully, about linear systems in relation to their non-homogeneous and homogeneous counterparts. Now, when you do this row reduced echelon form business, it's not just, oh, I'm just row reduced echelon, I just find the row reduced echelon form for the heck of it. Now, this gives me very specific, detailed information about not just the particular solution or a solution to the non-homogeneous system. Now it gives me everything. I'm able to always figure out what are the vectors in my null space of A, and what is a particular solution that works. So that's very interesting that this happens all the time, every single time that I find a row reduced echelon form. Okay. So now we know that. Okay. Once we have that understood, not only does the row reduced echelon form of a matrix tell us a lot about the particular solutions of the non-homogeneous system and the general solution for the null space. We also discussed this a bit, but I just want to reemphasize that the leading ones, which indicate the pivots, right? The pivots. This tells us a lot. This tells us, so just a note here. The row reduced echelon form of a matrix tells us which rows / column, just say row, which row column vectors are linearly independent. So we discussed this, right? We discussed in the beginning that this row with this row are linearly independent because they're not scalars multiples of one another, as you can clearly tell. But this last row here is a linear combination of the first two rows. So this last row is in the span. Since this last row is in the span, these three rows vectors together are not linearly independent. They're linearly dependent. So you have to get rid of the one, right? You have to get rid of this one that's in the span of the other two in order to create a linearly independent set. And these ones are referring to the first two rows. So the first two rows here, these vectors are linearly independent. Not only that, but if you look at it from the perspective of columns, that's also true. These columns here, as you can tell, they're also linearly independent because neither of them are scalar multiples of the other. But interesting enough, if you look at the columns, and you add up this column vector with this column vector, you get this third column vector. So do you see that? It's consistent both in the column version or in the row version of things. This last column is linearly is in the span of these first two rows, and this last column here, I should say this last row, this last column here is in the span of the first two columns. So these ones here, not only are they important to give us the pivot variables, these ones also indicate these are the places where the first row, the first column, second column are both linearly independent, or the first row, second column are linearly independent. So they also tell us about linear independence, which helps us finding bases, right? So if that's the case, then what's the dimension? So let me write this down. Let me write this one. Yeah, so it's symmetric. So what is the row space? I should say, what's the dimension of the row space of A? So we're continuing with this example here. A is this one. What's the dimension of my row space? So in the remember, I just said that the third row is linearly dependent if you include it with the three rows together, because this is in the span of the first two rows. So you would have to get rid of this. If you get rid of this one, you're only left with two linearly independent rows, and the row space is a linear combination of the rows. Do you understand? So the row space is a linear combination of the three rows, but one of them is linearly is in the span of the other two. So get rid of this one, and you still will have a linearly independent set that spans the whole row space. There's only two of them. So since there's only two rows that are linearly independent that spans all of the row space of A, then the dimension is 2. And the same thing goes for the dimension of the column space of A. It's also 2. So we have a new definition that I want to speak of. It's called the rank. Extremely important concept. The rank of A is equal, you can define it in many ways, is equal to the dimension of the row space of A, which equals the dimension of the column space of A. You can also define it as the number of linearly independent rows, or the number of leading ones in the row reduced echelon form. So it's equal to this. You can look at it this way, or you can look at it as the number of leading ones in row reduced echelon form, or you can think of it as the number of pivot variables. There's so many ways. To define the rank of a matrix. Okay. Very important concepts. So I want to do one more thing here, one example. So I want you to find the bases for the null space and row space of A. And I'll give you the A. 1, a -1, 3, 5, -4, -4, 7, -6, 2. So again, I want to find a basis for the null space and a basis for the row space. So then what's the first thing I should do? What should I do? So I want to know the basis for the row space and the basis for the null space. Find your variables, so try inverting first. Actually, no, now we're not so interested as much as before with finding the inverse. Now, like I said, we're going back to the basics, back to the beginning. We care more about the row reduced echelon form. So I'm gonna go back to my calculator. I got 1, -1, 3. Whoops, why did I do that? I got 1, -1, 3, 5, -4, -4, 7, -6, and 2. I'm going to take the row reduced echelon form of my matrix A. Look what I get. The row reduced echelon form of A is 1, 0, -16, 0, 1, -19, and I get 0, 0, 0. So, like I said, once you find a row reduced echelon form of a matrix, you know a lot about the nature of that system that it's referencing. So of course it's not written here, right? But really what we're saying is AX, we're really talking about this, guys. We're really talking about this for the null space, right? So what do we learn from the row reduced echelon form? Well, we know several things. 2 pivots. Okay, so if I have 2 pivots, what does these 2 pivots represent? 2 pivots represents 2 leading ones, right? We have 2 leading ones, as they call them. If I have 2 leading ones, what else do I know? I know that the first 2 rows and the first 2 columns are what? Are linearly independent. What else do I know? I know that the of A is 2. Okay, what else do I know? What else do I know? What else do I know? Well, if I have 2 leading ones and I had 2 pivot variables, how many free variables do I have? I got 1 free variable. See, all of this stuff, it's like getting a receipt, right? Like that's what the row reduced echelon form is. It's like a receipt of all the things, all the different transactions that you've made, that you can make, all the record history, like all the genetic code, like all of that is here. So I got two pivot variables, two leading ones. First two rows and columns are linearly independent. Rank of A is 2. We have one free variable. So why are these things important? Because if I know that the first two rows are linearly independent, then what do I know about the basis? What's a basis for the row space of A? What would be the basis for the row space of A? Well, the row space of A has a dimension of 2 because we have two linearly independent rows. Do you guys see what's happening? If I want to write it like this, 1, -1, 3, and 5, -4, -4. These two row vectors are a basis for my row space of A. I found it. How did I find it? By the row reduced echelon form. A lot of information there. Now, I took care of that. Now, how about the null space? How is the null space related? Well, if I have one free variable, what do I know about the free variable? It tells me what? The nullity, doesn't it? The nullity of A is 1. The nullity of A is 1. Now, how do I find what the basis is? How would I do it now? Now that I know the row reduced echelon form of A, how can I find it? How can I find the basis for the null space? I already know that the basis of the null space can only be constituted by one vector. Anybody that's with me? Anybody? Right. So once we have the row reduced echelon form of A, and I know this is referring to x1, x2, x3, right? x1 and x2 are the pivot variables. x3 is the free variable, right? So this is the x3, and this is x1, x2. So then from the row reduced echelon form, of A, what do we have? We got that x1 minus 16 x3 equals 0, right? And we have that x2 minus 19 x3 equals 0. Do you see why it equals 0? Because you can treat this as an augmented matrix 0, 0, 0. And if you do the row reduced echelon form, we still get zeros. So when you take the row reduced echelon form of A alone, embedded in it, it's as if you had a column of zeros. So you every single time you're doing a row reduced echelon form of a matrix, you're inherently solving the homogeneous system every time. I hope that makes sense. And so then this x3 must equal something, call it t. So that means that x1 is equal to 16t. That means that x2 is equal to 19t. And so then my matrix or my column vector is going to be 16t, 19t, t, which is t multiplied by 16t1. Again, this is the null space of A. So what's the basis? Basis for null of A, it's simply one vector, 16, 19, 1. Any questions about this? No questions. Okay. Now let's kind of look back a bit of what we've just done. The basis of row A is given by row space of A is given by these rows. Because we know that the first two rows are linearly independent, because we know that the ones appear, the leading ones appear twice in the row reduced echelon form. The rank of A is 2, the nullity of A is 1. 2 plus 1 is 3. What's so significant about that? Let's see another scenario here. We have two linearly independent rows given by the leading ones, which indicate that the row reduced echelon, that the rank of A here would also be 2. The nullity was 1. 2 plus 1 is 3. Let's see that if I get another one. Oh, here, the nullity of A has the, if the nullity of A is 2 here, as we know, what would be the rank of A here? Even though I don't have what A is. Right, the rank would be 2. Now, how do you know it's 2?
Because the nullity plus the rank equals the
Equals what?
the dimension
Of what?
of the space vector.
So that's something that you almost have. You're right. The rank would be 2. But why? What I'm trying to get at is a very important theorem in linear algebra. So in a sense, in a way, we've done all the stuff we've done. Everything that we've done kind of culminates and is summarized in one single theorem called the rank nullity theorem. So it's like given a matrix A with n columns. So given a matrix A with n columns, we have that the rank of A plus the nullity of A equals n. Very profound, very seemingly simple equation, but it's very rich as to why this is the case. The rank of any matrix, if you add it to the nullity of that matrix, that gives you the number of columns, n. So then how do you theorem makes sense because rank stands for independent matrices representing pivot variables and nullity represents the free variables. Yeah. Yes. That's right. Right. So then you know what? With this, I'm just going to write idea of proof. Okay. The number of columns of the matrix A when you represent when you're taking A as a coefficient matrix of a linear system, the number of columns, it's like saying the number of variables, right? The number of columns of A has to coincide with the number of variables of your system. And in a way, what we're saying, so number of variables, right? Remember the nullity, what was the nullity? The nullity is the number of free variables, right? And this is for a, particularly for a, it doesn't matter, but in particular, it's for a homogeneous system. That's why, if you recall, we talked about homogeneous systems in the beginning, but then we kind of like let off of it. We touched it, and then we let our gas. I don't know how to say the metaphorically correct. We just didn't pursue it any further, right? We talked about it and we just let it go. So the number of variables, now we're coming back to this though. So the number of free variables for a homogeneous system plus what? What does rank A tell us? It's the number of what? Number of pivot variables. There's only n variables to speak about. So in a sense, what we're saying is the number of total variables that exist can be classified into two distinct categories. We have either pivots or free. If you add these up, you get the total number of variables. But of course, it's beyond just the number of variables, right? Because the number of pivot variables embedded in it is the number of linearly independent rows and columns. You see how it's a little bit richer than just saying the number of pivot variables, even though this is one idea of proving it. But the number of pivot variables is associated with the number of linearly independent rows, which gives us the dimension of the row space, which is equal to the dimension of the column space. And if you add that to the number of free variables, the number of free variables indicates the dimension of the null space. So then there starts to become a bit more involved because now we're dealing with spaces, the row space and the null space. I don't know if you start to see that yet. But the row space of A with the null space of A, when you put those two spaces together, it gives you Rn. So with this theorem, basically what we're saying is that we can decompose vector spaces as a sum of two subspaces that have nothing in common except for 0. So that's a little bit more of the abstract theoretical bird's eye view of this. This is beyond just the number of free variables. The number of pivot variables gives us the number of total variables. Now we're able to discuss subspaces, in particular row space with the null space. You put them together and you get the codomain, right? It's because remember A is a representation of T going from Rm to Rn. And this Rn is the n that we're speaking of. This is the codomain. So the codomain can be decomposed as a union of the row space and the null space. Anywho. So that's why we discuss That's why we discuss row reduced echelon form from the very beginning. We stray away from it a little bit, but then we come right back because it tells us everything about the linear system. And now I think it's time to come back to this idea of equivalent statements. In linear algebra. We touched upon this also a little bit here and there, but now I believe we have a lot more to include. So I think we only discussed like 3 or 4, probably maybe 5 statements that are equivalent. So this only works for if A is an n by n matrix. So we're only dealing with square matrices, okay? So one of the first things we talked about matrices is that they can be invertible. So if A is invertible, what else is equivalent? Do we remember about this? Then AX equals 0 has only one solution called the trivial solution. And the trivial solution is X equal to the 0 vector, right? So what they're saying is, if you have an invertible matrix, hopefully we'll see how this follows from everything else, right? We also know that the row reduced echelon form of an invertible matrix is always what? So when we take a matrix and it's invertible, what do we know about the row reduced echelon form of every invertible matrix? It's always what? It's always the identity, right? Okay. Now, what else? Well, of course, if A is invertible, A inverse exists, right? That's what it means to be invertible. What other statements are true, are true? How about the determinant? If you have an invertible matrix, what about the determinant? Does not equal 0. Good. What about okay. So if the row reduced echelon form of an invertible matrix is the identity, how many column vectors are linearly independent? Well, this is an n by n, right? So then we have, do you see how it's equivalent? So to say the row reduced echelon form of A is identity, it means that A has n linearly independent columns. That's important. Why is that important? Well, then similarly, A has what? N linearly independent what? Yeah, column vectors, pardon me. Has linearly independent what? Row vectors, right? That's important too. If you have linearly independent column vectors, n of them, and you have n linearly independent row vectors, what else do you know about A? Remember, we defined something pretty recently that tells us the number of linearly independent columns and linearly independent rows. Does anybody remember? The basis has n vectors. Yes, 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 we have a full set of bases. We have n vectors. That's actually pretty good. So we can write that down. So the basis, but of what though? A is n. So yes, we can talk about that the column vectors. Yeah, we can write that. The a basis of Rn is equal to the set of column vectors of A or the set of row vectors of A. Okay. But what was that new terminology, that new definition that we have for the number of linearly independent column vectors, or the number of linear? Yes, that's what I'm looking for. So the rank of A is n. So remember, what does the rank also mean? It means what? The number of how many variables? What kind of variables do we have? The number of pivot variables. Wait a minute. So if we have n pivot variables, how many free variables do we have? 0. There are 0 free variables in homogeneous system. So if we have 0 free variables, what else do we know? What else is equal to 0? The nullity of A equals 0 by the rank nullity theorem, right? N rank A plus nullity of A equals n. In this case, rank A equals n, so the nullity must equal 0. Do you see that? Immediate. And this all stems from saying that the A is invertible. Now look, all these statements here are inherently the same. They all mean the same thing. They all cast, like, it's all a cascading list of true things. So if A is this, if A is invertible, then there's only one trivial solution for the homogeneous system. Then the row reduced echelon form of A is the identity. Then the determinant is non-zero. Then you have linearly independent columns and linearly independent rows. Then that means that it constitutes as a basis for Rn. That means that the rank of A is n, that there are 0 free variables because there's n pivot variables. And so the nullity of A is 0. All of this stuff, each and every statement is equivalent to the other statements. So if you have this, then you have everything else. If you have this, you have everything else. Everything comes as a complete package. And there's one more. There's actually several more things, but we're not going to touch upon that for now. The last one is the non-homogeneous system. Hold on, let me write this better. The non-homogeneous system AX equals B has a unique solution. That unique solution is A inverse B. And there's just one more for completeness of this. And last is related to the row reduced echelon form of A being identity, is that A can be expressed as A can be expressed as a product of elementary matrices. There's a few more statements that we can also speak about, dealing with the subspaces and how we can decompose a vector space into a sum of subspaces that are quote unquote complement to one another, complementary to one another. But we'll touch upon that after the exam. But this is it. This is all of the this is it, guys. So everything that we started with in the beginning is now have come back full circle, particularly with the row reduced echelon form. It's beyond just computing the row reduced echelon form for the sake of it. Now we have much more at stake. Now we can touch upon row space, null space. We can touch upon the fact that each of these spaces have bases, and we can find the bases based upon the row reduced echelon form, and it tells us exactly what vectors constitute a basis for these subspaces. Yeah, so it does take some time, to unpack the significance of certain things. So in the beginning, you just basically just following orders, and at first, I remember you guys had trouble with it, right? In the beginning. Also, how to distinguish that between row echelon form and echelon form. Remember that one problem we did in homework that took a while to understand. But now that you have that technical aspect understood, now we can talk about the more significant, theoretical, abstract significance of the row reduced echelon form. And now we're tying all the things together and putting them back and connecting them. So I hope you guys are able to see linear algebra from a more holistic view now.